Good morning. My name is Jim Fawcett. In this video, we're going to introduce the Rust programming language and we're going to focus on some of its models. So by model, we're talking about some kind of description for some particularly important part that helps us understand how the language works, what's going on, what's going to happen when we do something, write a line of code with the language. So this is the first in a short sequence of videos about Rust. And this morning we're going to talk primarily about getting started, installing stuff and doing a hello world and talking about the important features of Rust and so on. Let's start with a quick view of what Rust is, what Rust models we're going to talk about. So in this sequence of videos, we're going to talk about Rust type safety, a model for ownership, variables, the ability to generate objects, user-defined types, generics, and code structure. So in this video, we're going to focus on type safety and getting started and just what's Rust all about. Okay, so why Rust? Rust guarantees memory safety in that we're unable to create dangling pointers or null references. We can't read or write to unknown memory, and all of that comes about because of Rust's ownership policies. Programs won't compile if they're going to result in dangling pointers or the ability to read or write to unknown memory. There's some cases of having unknown memory that Rust can't detect at compile time, but the way it's designed, should you, for example, index outside of an array, then Rust does what's called a panic. It shuts down before you ever get a chance to read or write that memory. I'm going to show you in the next video after this one that C++ is very happily, happily allow you to do that. Well-designed C++ won't do that, but we'll get into those issues as we move along. So we get memory safety, and surprisingly, that same memory model helps us avoid data races. This is extraordinary. It's surprising that these memory model rules for single-threaded code also help us write data race-free code in a multi-threading environment. And so these are unique features of the Rust programming language. And that combines with excellent performance. Rust compiles to native code. It doesn't have a system of garbage collection. And so its performance is as fast as C and C++. And also, its level of abstraction is really good. It's right up there with C++ in providing us with good ways of hiding, low-level details behind abstractions. So, now this video, I'm going to assume that you haven't had any exposure to Rust, and so we're going to just talk about getting started for a little bit. So, if you go to the Rust site, rustline.org, you'll find a path to download the Rust environment, and that whole process is remarkably fast. In 7 or 8 minutes, you'll have Rust up and running. It's easy as that. And when you install Rust, you get the Rust compiler and also a really nice tool called Cargo. And Cargo wraps the compiler and has a bunch of other capabilities in that, it serves as a package manager. It can go pull resources, local resources and resources that are external, and even remote resources in a really nice, convenient way. And it also builds and executes code. And the installer by default will put cargo right on your path. So in any command window, you can pull it down and you can run cargo and build code and run it and all that good stuff. I would suggest you also install Visual Studio Code. I've given you a link to do that. I'm going to use Visual Studio Code here. Now, Visual Studio Code is not Visual Studio, okay? It's a much lighter weight. Really, it's a text editor more than anything else. It has some hooks to let you, for some languages, do debugging and compilation, but we're not going to do that. We're going to do all our operations in a command terminal in Visual Studio Code, but and we'll just use Visual Studio Code as a text editor. So so now we're ready, and so you know, if you the next part of the slides show that, but let's pull up Visual Studio Code and let's just do it, a little tiny bit of it. You know, I'm not going to do a lot of this because I don't want to slow down these videos. So here we are in a directory called GitHub, and I'm going to say cargo new hello. And that just created a, if you look here, here's hello, and it created a source file. So now in order to run anything, I need to move Visual Studio Code down into that folder. So let's just go into GitHub and we'll select hello. And now, let me pull up back the terminal. Okay, and now, so here we are in GitHub hello. Let's just say cargo run is building, and there's hello world. So what it just did was it built this file, a simple little file, you know, hello world. This is, and there's one other thing I want to look at, and that's cargo. Cargo is when I said cargo new, it built this package, and the package is really this directory, and well, cargo toml has some metadata, you know, about the package, the name of the package and its version and who the author is and all that sort of stuff. And if we had dependencies, which we don't now, but if we had dependencies on external code, we would put them here. And you'll see in later videos, you'll see some evidence of all that. So, you know, so here's hello world, and, you know, we can add a little bit just to convince you that this isn't all smoke and mirrors. So let's just change it a little bit. And now save it and run it. And you can see now it's spaced a little differently. It, you know, reacted to my changes. Now, what are we looking at here? So fn says this is a function, and here's main. So this is a normal Rust function. What we're looking at here is not a function, it's a macro. And you can tell that it's a macro because it ends in this exclamation point. People call it a bang. So it ends with this bang. And the issue is that for reasons we'll talk about in later videos, Rust functions aren't variadic. There's no easy way to make them variadic, but there's a very well-engineered macro system in Rust that makes it easy to generate macros that are variadic. We'll take variadic means they'll take an arbitrary number of arguments. So this println is a macro, and I can give it more arguments. So I could say here, for example, let's do this. Whoops. Now, this little squiggly is saying, hey, this isn't going to compile, but let's just say let name equals Jim. And now let's say hello world from, okay. So, so what I've just done is I've created a binding of this variable name to a value. And this happens to be a literal string, meaning it's stored away somewhere in the stack in a probably in the compiler's where in static memory where it puts the code, and so now it'll compile that. Now you notice that I got these little red squiggles before I had all that put in place, and that's because I have in my version of Visual Studio Code, I've installed a little helper, Rust RLS, that's developed by the Rust development team for Visual Studio Code to provide IntelliSense and completion, IntelliSense completion. So, and it works pretty well. There are some others I would recommend, at least when you begin. Don't just use RLS because sometimes they conflict and stuff. So anyway, let's just now I got to save this. You can set Visual Studio Code up so it automatically saves. I don't, because every once in a while I do the wrong thing if I've got it automatically saved. But let's just say cargo run. And now it said hello world from Jim. And I could add, let's add an from Jim, just to show you that I can take a variadic number of arguments. I'm going to say, comma, quote. Okay. And file, save all. And okay, and now this is again a literal string, and I could have named it and passed it in as an argument, but I'm passing this in as an argument. This literal string has gone here. This name referring to this literal string has gone here, so you can that's the way it works. So I'm going to stop with Visual Studio Code because this is taking too long. Let's go back to the slide presentation. And so, this is what we looked at. And, again, that's what we looked at. And so here's the cargo file, with the metadata and all that sort of stuff. And here's me building it. And here I added a different function, helper. And this is a reference. We're not going to talk a whole lot about that today, but in this video. But in the next video, we're going to talk a lot about the references. But anyway, I wrote a little helper function, and here it is. And in the next slide, I'm going to create an object. Now, this is just kind of a preview snapshot. There's a lot to talk about before we, you really understand how all this works. But Rust treats structs the way C++ treats classes. I can have data members in a struct. I can add functions to a struct. I can inherit from something called traits. Lots of good stuff. So here I have a helper that struct that has a string variable whose name is S, and I can create methods for it, function set string. And again, I'll be explaining all this stuff. This is just kind of a preview to a mind setting. You can so you can tell where we're going to go. We'll wait to the next video before we explain, you know, a lot about what's going on. But anyway, you know, so here I'm creating an instance as helper, and I say h.setString. I'm calling a method on that helper. So this is an object, okay, just, you know, same model as a C++ object, implemented differently, but the same idea as a C++ object. And now I can say print h.getString, and, you know, so cool. So why Rust? So Rust provides memory safety. I haven't really demonstrated that, but all of that's coming up. We're going to talk a little bit about it in the next slide. So it provides memory safety, freedom from data races, good performance, and you've begun to get a flavor for the abstraction, you know, nice function and object abstractions, just like, you know, all the modern languages. So type safety. So type safety is a model. Program is well defined if no execution can exhibit undefined behavior. And I'm going to show you a little snatch of undefined behavior in C++ in just a minute. You can't get that in Rust because of its memory model. A language is type safe if its type system ensures that every program is well defined, and that's Rust is type safe. A non-type safe language may introduce undefined behavior with integer overflow, buffer overflows, use after free, double free, race conditions, you know, all those kinds of things that malware likes to exploit, you know, you can't get in Rust. Okay, so here's an example of undefined behavior. There's a sequence of demos that I'll point to you in the next video. And in that sequence of demos, there's a couple of C++ demos. This is one of them. I'm demonstrating undefined behavior. So what I've got here is I have, so I'm assuming that you know a little bit about C++. So I have a vector, just a vector of integers named v. So I've created it, it's now empty. Now I set its capacity to 3, reserve, so that it will hold 3 things without reallocating. So a vector is like a buffer that manages its own internal memory. If you try to add another item, push back another item when its capacity is already full, it silently goes away, allocates new memory off, you know, in someplace else, copies everything over, you know, and you know, it's a silent operator. It's just like it has infinite memory. That's the good news. And the bad news is it silently goes away and does that stuff. Here, I push back, push back, push back. And so now I have reserved, I've filled up that entire capacity, and I create the, I take the address of V1, and I take the address of R1. Now, this is a C++ reference to the second item of the vector. Remember that we count starting from 0 with vectors. So this is a reference to the second item in that vector whose value is 1. And so I have the address of that location, address of R1 to show you that they're the same. The value of R1 should be 2, 1, 2, 3, because here's the 2. And so here it is. Capacity V is 3, 1, 2, 3. That's when I showed the vector. As a function that I'm not showing you here, but it's really simple. And here's the address of V1 and R1. They point to the same thing, okay? And the value of R1 is 2. It's just a second element of this vector. And now I do a pushback, and it didn't blow up. It just silently went away and allocated new memory, okay? That caused reallocation, 1, 2, 3, 4. address of V1. So here I'm taking the address of V1, and that's some same number. Address of R1, okay, is the old address, not the new one. It's the old one. So it's holding on to that old one. And now when I take its value, it's some garbage number, okay? I have read from memory that I don't own. And I could have written to it just as easily. Undefined behavior. Here's another aspect of undefined behavior. It's just a second part of the same program. I've created an array, okay, and now an array of 3 elements, and now I'm indexing from 0 to 3. Notice the equal sign. So I'm indexing 1 off the end of the array. Now the compiler's warning me, okay, but I can do it, okay, and so I did it. Okay, and now I'm just printing them out 1, 2, 3, garbage. So I'm reading garbage, and again, I could have written to that. And notice it exited, normal exit. Now, in all fairness, C++ has conventions that avoid all that. If I had used an iterator in that first part, back up here, if I'd used an iterator rather than a C++ reference, okay, when I push back 4, this is an invalid iterator, and as soon as I try to dereference that to get that value, it throws an exception, so I don't get undefined behavior. It doesn't give me a value, but that's the good thing, because I don't own that memory, so it shouldn't give me a value. It throws an exception. So C++, and the same thing for for that loop. If I use a range space 4, I'll never index it out of bounds. Okay, so C++ by convention has these nice ways of avoiding that undefined behavior. The real issue here is that in a large system, if I've got 3 million lines of code, and that's not large, the Linux kernel is 20 million lines of code or 30 million lines of code or something like that. And Windows is like 60 million or so. So, 3 billion lines of code is a modest sized system. And when you're writing a system that large in C++, it's extraordinarily difficult not to have 1 or 2 or 3 or 4 slips that generate that kind of undefined behavior, okay? Because you're doing this by convention. With Rust, it's done by construction. You can't have those undefined behavior. It's designed not to let that ever happen. You're going to spend a little more time with the compiler, because the compiler is going to natter at you when you do those sort of things. It's just not going to warn you. It's not going to compile. Okay, so with that, I'm going to stop this video. This is the end of this video. And the next video in the sequence, we're going to be talking about Rust ownership, the basis for the kinds of things we've been talking about this morning. So with that, I'll say goodbye.